Welcome to Chapter 13. We're discussing temperature and kinetic theory in this chapter. So temperature is a relative measure of the average kinetic energy of the molecules in a system. The faster the molecules move, the higher the average kinetic energy. If you've got two objects and they touch each other in such a way that they can exchange heat energy, they will, and they're said to be in thermal contact. So they're not insulated from each other, but they're allowed to exchange heat energy. Thermal equilibrium is reached when those two objects stop exchanging heat energy. Usually that's maybe an extreme example of it because it's an ongoing process. Heat energy will be exchanged, but you're at a level where your temperature is going to remain the same. So we say you're in thermal equilibrium. And this brings us to the 0th law of thermodynamics. So two objects are in thermal equilibrium if they have the same temperature and they're in thermal contact. Why didn't they name this the first law? Well, because they didn't think of it first. We have a first and a second law of thermodynamics, and then they thought of the 0th law. They said, wait a minute, we need to have something defined first before we talk about these other two. They didn't want to renumber everything, so we're stuck with a 0th law, that if you're in thermal equilibrium, you have the same temperature and you're in thermal contact. Thermometers, there are all kinds of thermometers. There are infrared thermometers that they're using now. Those are the touchless ones they talk so much about. They've been around actually for a very long time. They're just now in common use. But all thermometers work on the fact that some physical characteristic of a substance will change as the temperature changes. The old-fashioned thermometers that we're used to use volume or size changes. So those are the mercury and glass thermometers of my childhood, or alcohol in glass thermometers that you might see on the side of a barn someplace, or even bimetallic strips that are a part of your life, you just may not be aware of it. So in the bimetallic strips, what we have is you have two pieces of metal. In our example, we have brass and steel, and they're bonded to each other. Brass expands the most on heating. So if you heat this strip up, the brass part is going to have the larger volume, and that makes the strip curve down. If we cool it off, anything that expands the most on heating will contract the most on cooling, so it curves the other direction. You see these in thermostats in homes, you see them in thermostats in radiators, in automobiles, and all kinds of other places. If sometimes the thermostat is made out of a coil of metal that's a bimetallic strip, and you can hear it click as it makes and breaks contact. So this is a bimetallic strip regulator that's probably part of some sort of thermostat. So you have the darker blue and the lighter gray, two different kinds of metal. If the blue, if the gray expands the most on heating, when this is heated, this bimetallic strip will actually curve up and make contact, and when it's cooled, it'll bend the other way and move away from it. And that making and breaking of contact is going to send a signal along this wire and turn on and off something. Maybe it's your air conditioner or your heating system, or maybe it's something else altogether. There is a demonstration using a bimetallic rod and a lighter, and we'll do that probably in lab. We can use color changes to indicate temperature changes. This usually involves liquid crystals. They respond to temperature by changing color in a very limited range. So they don't have the versatility of a mercury and glass thermometer, or an alcohol and glass thermometer. It used to be, before these touchless thermometers that use infrared radiation became so popular, you would see in daycares and kindergartens, they'd put a little strip, like a little Band-Aid, on a child's forehead, and it was to be used to detect a fever. And it, again, you only needed a limited range. You also sometimes see these on aquariums, again, because you want to maintain the water in a very narrow range of temperatures. There are electrical resistance thermometers out there. The electrical resistance of a wire changes with its temperature. This is a meat thermometer for grilling, but the kind of digital thermometers that you stuck under your tongue also are electrical resistance thermometers. We use 3 different temperature scales. We use the Kelvin, the Celsius, and the Fahrenheit. Some of these used to have different names. Fahrenheit has always been Fahrenheit, but Celsius used to be centigrade, and Kelvin used to be referred to as the absolute temperature scale, until physicists got together and said, hey, all the temperature scales ought to be named after people. And so they changed centigrade to Celsius and absolute to Kelvin, and there we are. So water boils at 212 degrees Fahrenheit, which is the same as 100 degrees Celsius, which is the same as 373.15 degrees Kelvin. If I blew this up enough, you would notice that Fahrenheit has a little degree sign on it, Celsius has a little degree sign on it, but Kelvin does not. I probably will include one just to be redundant, but it's technically not supposed to be there. So, highest temperature ever recorded in the US, ooh, I don't know if this is accurate or not. So we'll move on to something I know is accurate, which is the freezing point of water, 32 degrees Fahrenheit, 0 degrees Celsius, 273.15 degrees Kelvin. 0 degrees Fahrenheit is equal to negative 18 degrees Celsius is equal to 255 degrees Kelvin. You can see they've got a temperature for the moon, and here is absolute zero. So absolute zero is 0 degrees Kelvin, which is minus 273 degrees Celsius, or minus 450, looks like, degrees Fahrenheit. All right, just to give you some sense of how the temperatures vary. One thing you should notice is that a Fahrenheit degree is about twice the size of a Celsius. They're about twice, half the size. I'm sorry, Fahrenheit degrees are half the size of Celsius. So a 1 degree change in Celsius corresponds to approximately a 2 degree change in Fahrenheit. So we've already said that the freezing and boiling temperatures. Fahrenheit scale was devised in the early 1700s. Fahrenheit was a German scientist. The story surrounding it is that he used outside air temperature for 0 degrees, and he used his wife's body temperature for 100. So knowing that, she had a slight fever, and it was really cold that day in Germany. The Celsius system was devised to have a more logical progression. Your wife's body temperature doesn't seem to be a good thing to be 100. So for the Celsius, they used water. In science, we use water a lot for our standards. So water freezes at 0 degrees Celsius and boils at 100. And then, of course, the Kelvin, or the absolute temperature scale. We devised this in an effort to get down to a point where we thought there would be no more molecular motion, but we're not so sure of that anymore. We now believe that there is molecular motion at temperatures colder than 0 degrees Kelvin. It's just molecules move really slowly. You do not need to memorize these 3 conversion equations. They're just there for reference. The Kelvin scale is based on the triple point of water, so that's the single temperature and pressure where water will exist in all 3 phases, solid, liquid, and gas. And you can see about the lowest temperatures measured in a lab and then outside the US. And if you go to Antarctica, that is as cold as it gets. Although with global warming, who knows? This is a diagram from your book, figure 13.6 from the textbook. And you can see again, it compares the different temperatures. If you measure it in degrees Celsius and degrees Kelvin, if you're measuring a temperature change, a delta T, you don't have to care because they're exactly the same size. But if you're looking for a value like the boiling point of water, then you have to specify the unit. But temperature changes in absolute or Celsius are the same number. And you can see it's about 9 degrees Fahrenheit is equal to about 5 degrees Celsius. Almost a 2 to 1. Let's talk about the thermal expansion of solids and liquids. So most objects increase in as they increase in temperature, they will expand because of the motion of the molecules. The equation for expansion in one dimension is delta L is equal to alpha L sub 0 delta T. Delta L is the change in length, so that's final minus initial. Please remember that. L sub 0 would be your original length. Delta T is the change in temperature. Again, final minus initial. And alpha is the coefficient of linear expansion. It has units of 1 over degrees Celsius, or degrees Celsius to the -1, if you want to write it like that. If you're changing in volume, the change in volume is equal to beta times V sub 0. It's delta T. So delta V is the change in volume, V sub 0 is the original volume, delta T is the change in temperature, and beta is the coefficient of volume expansion. And again, in 1 over degrees Celsius. So if you have an isotropic object, and that's one that expands uniformly in all 3 directions, then beta is the same thing as 3 times alpha. This is a photograph of the expansion joints on probably a bridge. You can see that it looks a little bit like a zipper. So this is to keep the bridge from buckling under high temperatures. When it gets hot, the metal will expand and the gap will reduce. When it gets cold, the metal will contract and the gap will increase, but it will always remain a solid. And again, this is from the book. And this is an example of a pothole. So potholes happen when water gets into cracks, freezes and expands and breaks the asphalt up. And the end result is that over a long, cold winter, you have a lot of potholes. Water is a substance that is most dense as a liquid, and that's why ice floats. Ice is going to float. Yay for that, otherwise the poor fish in the lakes that do freeze in the winter would be smushed. All that freezing and sinking of ice would be terrible. So this gives you some idea of the density of fresh water. It is also a graph from the textbook. So you can see most dense at about 4 degrees. And that gets us to some of the gas laws. So the ideal gas law is that PV equals nRT. P is pressure, V is volume. Little n is the number of moles. Capital R is the universal gas constant. It's a number. You don't need to memorize it. It'll always be available for you to look up. And capital T is the temperature. The temperature needs to be in degrees Kelvin. The temperature needs to be in degrees Kelvin. If you think you're not going to remember that, you need to write it down. Pressure will be in pascals or newtons per meter squared, and volume will be in cubic meters. In physics, we don't usually work with moles, so we would rewrite it as PV equals capital N times K times T, where capital N is the number of molecules in the gas and little k is something called Boltzmann's constant. And again, it's a number we would just look up. There is a relationship between Boltzmann's constant and the universal gas constant, but you're not going to have to go back and forth. It's enough if you know PV equals nRT. So let's talk about that, because I'm not going to ask you to do math with it. We're going to just look at relationships. So suppose we hold the pressure constant and increase the temperature. So PV equals nRT. We hold the pressure constant, but the temperature goes up. So pressure is constant. We want to know what happens to the volume. That's why there's a question mark there. Little n is the number of moles. It's a constant. Capital R is a constant. And we said we're going to increase the temperature. That's why there's an up directing arrow. If everything on the right-hand side is held constant or goes up, then that means that anything that's free to change on the left-hand side also has to go up. So that would be the volume. The kinetic theory. The average kinetic energy of a molecule can be calculated. There's a formula for that. It's related to Boltzmann's constant and the temperature, or if you don't have that, you can do it with the velocity and the mass. Because kinetic energy is mv squared over 2. Sometimes you can take the equation and rearrange it and solve for the root mean square velocity. So that's abbreviated little v and then a subscript RMS. And so we have an equation that has a square root sign in it. So let's look at how speeds are distributed. You can see that there is the most probable speed, the one that occurs most frequently, and there is the root mean square. The root mean square is a little less than the most probable. And you can see as you move away from the most probable, you have fewer and fewer occurrences, fewer and fewer molecules moving at that speed. This diagram is a Maxwell-Boltzmann distribution of the molecular speeds in an ideal gas. And again, it's just showing you that a lot of speeds are possible, just some are more possible. Phase changes. So when you change phase, when you go from a solid to a liquid or a liquid to a gas, a PV diagram can be very helpful. So let's look at our diagram. So we have a series of pressure versus volume diagrams for different temperatures. And you should notice that there are certain points along the way that we want to talk about. So you have the liquid region and the vapor region, and you have lines separating them and something called the saturation curve. The critical point is important. It's a place on your PT diagram, so pressure temperature diagram, even though it's also on the pressure volume diagram. But it's a place on the pressure temperature diagram that defines a temperature above which the liquid phase cannot exist. So on a PT diagram, the triple point's the point where all three phases are in equilibrium. So let's look at this phase diagram for water. Again, water is our favorite substance. So this diagram you do need to be able to identify points on. If I drew the diagram and left out the words critical point, triple point, S, L, and V, you ought to be able to figure things out. I wouldn't even have to give you the numbers, just the general shape. So everything to the far left at the very lowest or coldest temperatures is the solid. S stands for solid. So anything to the left of this, what we've got is a red line, is in the solid phase. Solid, 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 all the way down solid. Anything in the little cradle part, the little U shape, is in the liquid phase. And everything on the right side of the curve, which goes to the hottest areas, is in the vapor or gas stage. Where all three lines come together is the triple point, and the highest point on the far right-hand side is the critical point. Remember, back here, the critical point's a place that defines the temperature above which you cannot have a liquid. Okay, I typically will draw this diagram and ask you about the 5 different places. So this area where it's a solid, the middle where it's a liquid, the far right-hand side where it's a vapor, the triple point, and the critical point. So liquid and gas phases are in equilibrium at boiling. What that means is that as you're boiling a pot, if you put a pot of water on the stove, the temperature goes higher, higher, higher until you hit the boiling temperature, and then the temperature will not change until all the water has boiled away. And then if you add heat, any steam can get hotter. So the liquid and gas phase are in, excuse me, equilibrium at the boiling temperature. And the vapor pressure is the pressure at which your gas can coexist with its solid or liquid phase. And that vapor pressure depends on both the substance and the temperature. So let's look at how that relates to humidity and evaporation and boiling. So with humidity, relative humidity tells us how much water vapor is in the air compared with the maximum possible. So as you know, if you have a high relative humidity, it feels really muggy outside. If you go out to Arizona, and it's got low relative humidity, it's going to feel very dry. And in fact, you may notice that you don't really sweat, that the moisture, when it reaches your skin, tends to evaporate almost immediately. So relative humidity is dependent on the air temperature. Warm air can hold more moisture than colder air. And your dew point is the temperature at which you reach 100% relative humidity. So if you try to add more moisture to it than that, it can't happen. And water leaves the air. A molecule will leave a liquid when it has enough kinetic energy to escape those intermolecular bonds, those forces holding the water molecules together. This happens when water boils and when water evaporates. Both of those processes, boiling and evaporation, carry they carry molecules away from the liquid, and they also remove energy in the process. The energy goes with the vapor molecules. So let's look at boiling. This is an exaggerated drawing of it. So here's a container. This big circle is a gas bubble at the bottom of the pot. We have our liquid. Atmospheric pressure is pushing down. The liquid is pushing down. So you've got two things pushing down on that gas bubble, the atmosphere and the liquid. As soon as the pressure inside the gas bubble is bigger than the liquid pressure plus the vapor pressure, you will have boiling. And boiling pressure and volume are related by PV equals nRT. So boiling is going to be determined, your boiling temperature is going to be determined by your pressure. At a high altitude, you go up, 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 we're climbing a mountain. You have low atmospheric pressure. So as the pressure goes down, 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 the boiling temperature will also go down. The higher in altitude you go, the lower your boiling temperature. The closer to sea level you get, the higher your atmospheric pressure, the higher the boiling temperature. It's about 10 degrees Celsius for every 10,000 feet. So every 1,000 feet would be about 1 degree. So at sea level, water will boil at approximately 100 degrees Celsius. If you are 10,000 feet above sea level, it'll boil at 90. If you're 20,000, it'll be only 80 degrees Celsius. Climb Mount Everest, it's higher than 20,000 feet. Water will boil at an even lower temperature. And just here's a graphic to give you more details. Only here they have the boiling temperature in degrees Fahrenheit, not Celsius. So a pressure cooker, you might know these as Instapots. They reduce cooking time by increasing the boiling temperature. So what happens is you have a really tight lid and a pressure regulator so that the pot doesn't blow up. And as the pressure increases, the boiling temperature will increase. And the hotter you get the food, the quicker it's going to cook. So at a high altitude, without an Instapot or a pressure cooker, food has to cook much longer to have the same degree of doneness. So if you're boiling eggs, an egg that's perfect at sea level, boiled for 3 minutes, will not be perfect on the top of Mount Everest. It will be undercooked. The higher you go in altitude, the longer you're going to have to cook food that's boiled, because you have to compensate for that lower boiling temperature. Evaporation. So, liquid evaporates when the molecules have enough kinetic energy to escape those intermolecular bonds. So if you've got water on your skin, you've been sweating, or you've just come out of the pool, as the water evaporates, it removes heat energy from the liquid, so from your body, and that cools you down. If you put alcohol on your skin and it evaporates, you notice a cooling sensation. Again, if you get out of the pool or the ocean or wherever, the lake, and the water is on your skin, as it evaporates, it cools you off. If you sweat, as the water will evaporate, it will cool you down. I've known a couple of people in my lifetime that didn't sweat, and they were always miserable when it got over about 70 degrees Fahrenheit outside. So for practice, be sure to practice those expansion and contraction problems for length, the linear coefficient of expansion. There's some in the study guide. If you need help with them, let me know.